Hello everyone, I am Rémi Watrigant and I will present our iCal paper called Twin Widths 3, Max Independent Set, Mean Dominating Set and Coloring. This is a joint work with Édouard Bonnet, Colin Geniet, Jung and Stéphan Thomassé. So as the title suggests, this is the third paper of a series devoted to a new graph parameter called twin widths. So before I present you the new results of this paper, let me briefly introduce what twin width is. So twin width is a graph parameter that is an integer value which is defined for every graph. And at the heart of this new parameter is the concept of contraction sequence. So start from the graph itself and perform a sequence of contractions. What we call a contraction is the fact of taking two vertices, no matter whether they are adjacent or not, and identify them in order to create a new vertex. So in this example, we will start by contracting E and F in order to create a new vertex EF. The new adjacencies are as follows. If a vertex is adjacent to both E and F, like C for instance, then C will be still adjacent to the new vertex EF. Now if a vertex is adjacent to only one of E or F, like A for instance, then A will be adjacent to EF, but with a red edge, remembering this error. So we can see that D is also adjacent to E but not F, so there is a red edge as well between D and EF. So along this contraction sequence, red edges will appear. We will thus deal with what is called trigraphs, graphs where between two vertices there is either no edge, a black edge, or a red edge. So we continue this contraction sequence by contracting A and D. So B will be adjacent to AD with a black edge, while G will be adjacent to AD with a red edge, just like EF. Then we will contract B and EF. In that case, we need another rule to decide the adjacency between AD and BEF. This rule will be that red edges are absorbing black edges. So there will be a red edge between them. So we continue this contraction sequence until we reach the graph with only one vertex, A, B, C, D, E, F, G. So if we summarize what is the general rule when we contract two vertices, U and V, remember that U and V don't need to be adjacent. So we can say that all private neighbors of them will be connected with red edges. And for common neighbors of them, red is absorbing, which means that a vertex will be connected with a black edge only if it was connected with a black edge to both U and V. So what is twin width? The twin width of G will be the least integer G, such that G admits a contraction sequence where all trigraphs have maximum red degree at most D. So in our example, we can see that the maximum red degree never exceeds 2. So we say this is a 2 sequence, or a 2 contraction sequence. It means that this graph has twin widths at most 2. And the twin width of G will be the least maximum red degree among all possible contraction sequences. Another convenient way to see a contraction sequence is as follows. We start from Gn, which is G, and has only black edges. Then we apply our contractions. At any point of the contraction sequence, Gi has I vertices. And each vertex u of Gi can actually be seen as a subset of vertices u of G of the initial graph G. Now, if you take two vertices u and v in Gi, then depending on the edge between u and v, we have the following situations. If there is no edge between u and v, then there is no edge in G between u of G and v of G. If there is a black edge between u and v, then there are all possible edges between u of G and v of G in G. If there is a red edge between u and v, then there is at least one edge and at least one non-edge between u of G and v of G in G. And finally, at the end, we get G1 having only one vertex u, such that u of G contains all vertices of G. So a natural question is, which graph classes have bounded twin widths? In the first paper of the series, we showed that actually many different classes have bounded twin widths. It contains bounded rank widths, and thus bounded clique widths, and even bounded Boolean width graphs. So we can also mention unit interval graphs, which have unbounded rank widths, but also proper minor closed class, which include planar graphs, for instance, and many other classes. So basically, any resultant bounded twin width graphs will apply to all these classes. So we will be able to generalize some known results in a unified way. So in this new paper, we have 4 different kinds of results, all using this contraction sequence that I presented. Efficient parameterized algorithms, approximation algorithms, polynomial algorithms, and some will have consequences on structural aspects on bounded twin width graphs. So let's start with some parameterized algorithms. So in twin width 1, we proved the following very general result, that first order model checking is FPT parameterized by the size of the formula and the twin width of the input graph if a contraction sequence is given in the input. This allows to prove that many problems are FPT in bounded twin width graphs, like for instance the classical k-independent set problem, because you can encode the problem with a first order sentence. So this sentence means that there exist k vertices, x1 up to xk, such that they are both pairwise different and pairwise not adjacent. So you can encode many other classical problems like k-clique, k-dominating set, subgraph isomorphism, induced subgraph isomorphism. Unfortunately, the running time of this algorithm is terrible. It is a tower of exponentials in both k and the value of the twin widths. This terrible running time is mandatory if we want to capture all first order, because there exist first order formulas which require a tower of exponentials even in cographs which have twin width 0. However, we can ask for particular problems whether there exist more efficient algorithms. So we answered this question positively in the paper by obtaining single exponential algorithms for several problems such as independent set, clique, dominating set, or natural generalizations of them. So when I say single exponential, I mean that the twin width is considered as a constant, but the hidden constants are not huge. For some generalizations of these problems, we were able to obtain 2 to the k log k times n algorithms in bounded twin width graphs. So this is important to note that all these algorithms need a contraction sequence in the input. But for all known classes having bounded twin widths, there is always an algorithm producing such a contraction sequence. So let me sketch how the algorithm works for the k-independent set problem. So finding an independent set of size at least k. So you consider your D sequence from Gn to G1, and in each step you compute a best partial solution in each connected red-induced subgraph of size at most k. So since it is a D sequence, all red graphs have maximum red degree. All red graphs have max degree at most D. So the number of connected red-induced subgraph is at most D to the power of 2k times n, which is single exponential in k. So this is the dynamic programming algorithm, and at the beginning, in Gn, since there is no red edge, the connected red-induced subgraphs are singletons, so computing the solution in each is obvious. And at the end, G1 contains all the vertices of G, so we indeed solve the problem. So it only remains to show how to go from Gi plus 1 to Gi. So when we consider a connected red-induced subgraph, like for instance the one with gray points, we want a solution intersecting each of these bags. So in the previous step of the sequence, if Z is the result of contracting U and V, it means that the solution intersects either only U or only V, or both U and V. And for each of these three choices, we construct a solution from the previously computed solutions. For instance, if the solution intersects only V, then we consider the connected red-induced subgraphs formed from all previously chosen bags minus U. By the definition of our sequences, since the red degree of U and V is at most D, there will be at most D plus 1 connected red-induced subgraphs to consider in the previous steps. So we consider these connected red-induced subgraphs, T1, TQ. The crucial point why we only need to consider red edges is because we cannot have a black edge between bags which are concerned by the solution we are looking for, because the solution would not be able to intersect both these two bags, since there are all possible edges between them. So if there is a black edge between a Tx and a Ty, then we can immediately discard this choice. There is no solution intersecting all gray bags if it intersects V but not U. We can also discard this choice if there is no solution for some Tx, because it has been discarded before, maybe. So if it is not discarded, we simply take the union of solutions of all T1 and TQ. So an interesting fact about this algorithm is that it readily generalizes the classical algorithm we have for cographs, which are exactly graphs with twin width 0. In the case of cographs, we have no red edge, so it simply consists in taking the union of solutions or the max of solutions depending on the black edges. Concerning generalizations such as the weighted version of independent set or induced subgraph isomorphism or subgraph isomorphism, the increase of running time 2 to the k log k instead of 2 to the k comes from the fact that in the dynamic programming we not only need to decide the solution with non-empty intersection with the gray bags, but also roughly how many vertices we will pick in each of them. So basically we need to cut the parameter k into many pieces, which costs k to the k. So now let's consider the second point about structural aspects of bounded twin-width graphs. So more precisely, we will prove that bounded twin-width graphs are chi-bounded. So what is chi-boundedness? So for a graph G, chi of G denotes its chromatic number, and omega of G denotes the size of a maximum clique. Since each vertex of a clique has to receive a different color, we have that chi of G is greater than omega of G. The other direction is false in general, since there exist triangle-free graphs with arbitrary large chromatic number. So now a graph class is chi-bounded if there is a function f such that for any graph G of this class, the chromatic number of G is at most f of the size of a maximum clique of G. So still using our D sequences, we were able to prove, with a quite simple proof once again, that bounded twin-width graphs are chi-bounded. That is, they can be colored with at most D plus 2 to the power of omega of G minus 1. And this coloring can be found in polynomial time if a D sequence is given. And as we will see, we roughly have to follow a greedy argument. So this generalizes and simplifies the proof for bounded rank width classes. However, the function f we have here is exponential, and it is still open whether bounded twin-width graphs are polynomially chi-bounded. So let's see quickly how it works for omega equals 2, that is triangle-free graphs. We can show how to color these graphs with at most D plus 2 colors. So the algorithm uses the D sequence backward. So it starts from the end, G1, having only one vertex that you can color. Then you go backward. So there is a vertex Z, which is split into two vertices U and V. So one of these two vertices can take the same color as Z. But the question is, which color can we use for the other one? So there are two possibilities. Either Z has only red neighbors. In that case, it has only at most D neighbors, and thus there will be an available color smaller than T plus 2, D plus 2. In the other case, Z has at least one black neighbor. But in that case, observe that there cannot be an edge between U and V, since otherwise there would be a triangle in our graph, which is impossible because we are in the triangle-free case. So we can actually use the same color as Z, and we are done. So I will now mention the other results we have in the paper without too much details. So the first one is about shortest path-like problems. For these results, we still use our contraction sequence, but we use them in order to partition the edges of the input graph into a linear number of bicliques, each side of which is on consecutive vertices with respect to the contraction sequence. So this allows to obtain algorithms with a better running time than in general graphs for single source shorted path, all pairs shorted path, and diameter. The last kind of results we have is about approximation and about the minimum dominating set problem. And for this part, we use a branching version of the contraction sequence called versatile tree of contractions, which has been defined in the paper Twin-Width 2. So using these more complex objects, we are able to prove that the integrality gap of dominating set is bounded by a function of the twin width only, which implies a polynomial time approximation algorithm. To conclude, let me present you some open questions. The first one is perhaps the most important one. All presented algorithms require the contraction sequence as input. As said previously, for all known graph classes which have bounded twin widths, there is an algorithm for providing this sequence. But what is missing is an algorithm which, given an arbitrary graph, would output a contraction sequence with a twin width value not too far from the optimal value. So for instance, an FPT approximation. The second one is about chi-boundedness. We proved that bounded twin width graphs are chi-bounded, but this is still open whether they are polynomially chi-bounded. This will generalize the same result for bounded click width graphs, which was recently obtained. Something that I didn't say is that bounded twin width graphs satisfy the strong Erdős-Einhard property, which is a first step for polynomial chi-boundedness. And the last one is about approximation algorithms in bounded twin width graphs. We proved that dominating set has a constant approximation. Does it admit a p-TAS? And even a constant approximation, whose ratio does not depend on the twin widths, is open, actually. And finally, any constant approximation for independent set is also open. And we note that such an approximation algorithm would imply a p-TAS by a classical gap amplification argument. So the last section of our paper contains many other open questions, so don't hesitate to have a look if you're interested. Thank you very much for watching. Bye bye.